All right, good morning. Welcome back. It's another Monday, but it's the second to last Monday of quarter three. So we have a 5-day week this week. And then we've got some review and then some finals on next week. And yeah, so this week's stuff is covalent bonds. We did a lot with ionic bonds last week. I got some questions over the weekend about polyatomics and what even is going on with polyatomic ions. And that is all super valid and true. And I'm thinking we'll take the polyatomic ions another step next quarter, which seems so far away right now, but they will kind of work really well with another thing that we do at the beginning of the quarter. So that was kind of just a little, like, the idea there was introduce you to a concept that I will introduce you to sometime, and I was hoping that the Kahoot might be, like, interesting and fun. I was getting some thoughts on how it's not when there were a few things that were not on your page, and I get it that that's frustrating. So maybe I should notice. The one that I've used forever and ever and ever is gone now. So it's like, this one's pretty close. It asks you about mercury, which is a little bit not a thing because mercury has variable charge like all transition metals. Okay, so if you did the Kahoot and you were like, oh my gosh, I can't stand this, I'm sorry. That might have been too frustrating, or like unnecessarily frustrating, I guess. Okay, so attempt at like game over the weekend, maybe not so successful. Okay, so we'll leave that there. We won't do more Kahoots for now. At least we might decide to upvote them when we are in person. I'm not sure, and I let you vote in situations like that. However, we can't do that virtually. Okay, let's just get into our last bit of stuff. So anyway, so I know that I'm leaving you on the cliffhanger of like, okay, I know that this is a carbonate, but I don't know how to form a compound with that yet. But if you want the preview on that topic, the preview looks somewhat like that you actually do kind of know what to do with that. Because even though this is a polyatomic with lots of atoms in this ion, it's a charged particle, it's an ion, it's similar to, so this is a carbonate. You've seen other ions with a charge of 2 negative. Charge is key to everything. Charge is key. So, for example, if you're working with some other ion with a charge of 2 negative, you can do like stuff that you can do with a single atom with a charge of, whatever charge, you can also do with a polyatomic ion. Right, 2 minutes. So you know now that you can do things like, this is just a little bit of a review, but you can do things like this sodium carries 1 positive charge, this oxygen carries 2 negative charge. You can do the math way or the crisscross way. You're going to need 2 1 positives to balance out 1 2 negative. Same thing, even if it's polyatomic. Same idea. This sodium is still 1 positive. This carbonate, that polyatomic, is 2 negative. That's not neutral. 1 minus 2 is not 0, but 2 minus 2 is 0. 2 positive charges will neutralize 2 negative charges. And you write that by saying 2 sodiums, which are each 1 positive, will neutralize carbonate like that. That would be sodium carbonate. Okay, but today's lesson is not about charge. Today's lesson is about covalent bonds. So let's do it. Okay, so covalent bonds. So things that we are going to do with covalent bonds in the next few days, we're going to learn how to draw them. We're going to learn how to name them and formulas. There are lots of names and formulas that we won't do. We will do kind of the simplest form, which is great for this class. I will let you do all of the more complex things later because a lot of it is antiquated and just rote memorizing. And then the other thing that I want to do with you is get you some of the three-dimensional structures. This is a unit a week where we typically build a lot of models. We don't have any of those things with us, so I'm going to show you a video instead. And the video has a bunch of 3D models. The human in the video, I think, makes great chemistry videos, and has like built all this stuff and has all of this stuff to show three-dimensionally. So I'm going to teach you about 3D structures through someone else's video, which feels wild, but it'll be okay. I want to get you through the same stuff that I would get you through if we were in the classroom, even though we don't have the model kits. So we'll call them Vesper shapes. Are these 3D structures? This is the same thing. The 3D structures are called Vesper shapes. And I want you to start thinking about polarity. So you may have heard of polarity in biology class or in magnetism is all about polarity. When your fridge magnet sticks to your fridge, you've got like positive charges, negative charges, opposites attract, blah, blah, blah. Here we're going to be thinking, does the shape that we're looking at have a side? We're going to think like the Earth poles, and like Earth is a giant magnet. So on Earth, we have one side that's different from the other side, and that's what lets us use a compass. We have a north side and a south side. So we're going to start looking at our shapes and saying, is there a pole? Is there a side that's different from the other side? If there is a pole, then the molecule will behave differently than if there is not a pole. So if the molecule is exactly the same on all sides and there's no side different from any other side, then basically, actually we can do this quickly. Basically, if your molecules have poles, then they will act like magnets and they will stick to each other. So you can get them lining up with, this south side attracted to this north side, this south side attracted to that north side. You get this, like, this is not a very good drawing, but like, you get this magnet effect of opposites attracting if you have a magnet type thing, a polar type thing in your molecule. Whereas if there's no pole and no kind of like magnet pole thing going on in your molecule, then there's no polar attraction. There are other things that kind of happen, but they're super weak. It's like if you try to stick a piece of paper to your refrigerator, it's not going to stick because there's no magnet in it. But as soon as you get the magnet, now they're sticky to each other. So this is like two pieces of paper stuck to each other, which like obviously is not going to work because there's no force sticking them together. Okay. So to rewind just a little bit, covalent bonds this will be kind of the point that we get to in terms of covalent bonds, is this polarity stuff. Yeah. Yup. Okay, so we're gonna start here and we're gonna end there. Great. Now I've summed up your whole week. Okay, good. Let's do it. Okay. Covalent bonds. Actually, let's even start with some concepts before we start drawing them, because that makes sense. Concepts. Covalent bonds. Concepts, but maybe even before that, all the bonds. Here's your periodic table. Okay. We know that the metalloids are kind of here. Metalloid staircase. We know that the metals are over here. Everything over here are metals. We know the non-metals are over here. Okay, you may have put this together while we were doing ionic bonds. Ionic bonds are a metal plus a non-metal. So, okay. We're going to abbreviate, but it's going to make sense. Not always the case. Metal is M, non-metal is not M. Okay, so ionic bonds are a metal plus a non-metal. Ionic bonds tend to be very they're either aligned or they're not aligned. So ionic bonds form a structure kind of like this. If this is sodium chloride or whatever, they're gonna form like a crystal is the shape that we call this, and this kind of pattern replicates for the entire thing. So rock frequently has an ionic type structure. This is the kind of thing where if you hit it with a hammer and like a little bit of drying will like totally break it, that's an ionic type structure, because once you hit it just a little and shift it just a little, now you've got a positive thing lined up with another positive thing, a negative lined up with another negative thing, that's gonna blow itself apart. We call these crystal structures. And you see crystals with those really, really flat edges. That's another ionic type thing, and that has to do with that same like sheet property. Once we displace those sheets a little bit, it totally breaks. Those are ionic type things. They also have super high melting points. Like if you're trying to melt a crystal, if you're doing this in a lab, which we do not have equipment for, which is great because melting crystals is like uncomfortable. It's one of those things that you do that is like very unpleasant, but you do it because you have to. And so you sit over this little tiny machine and you put your crystal in this, like it's like a needle almost, and heat it to like 800 degrees. So like here you are behind your desk with this thing at 800 degrees in front of you, and you have to stick your eye on a microscope to watch the moment when the crystal goes and turns into a liquid. It's super okay. So ionic bonds, crystal structures, high melting points, stuff like that. And they're all these little charged little ions, like all of our ion stuff, all charged particles. And they dissolve in water really easily. Okay, dissolve in water. So these things have charge. The end point of our covalent stuff is looking at charge also. I drew this as a magnet because that's something that you have a better sense of in your brain, probably a fridge magnet than like a charged particle. But actually, it's the same thing. This is not a magnet. This is not actually north-south. It's exactly this kind of deal. So here's a hint to the future. Ions dissolve in water. Water must have properties similar to ions. Even though water is covalent, it's got some properties similar to this kind of structure. Okay. Well, actually, before we get to covalent bonds, let's do a tiny bit on metallic bonds. Metallic bonds, there are 3 types of bonds. Ionic is metal and nonmetal. Metallic, make a wild guess, metallic bonds are between 2 metals. Okay, so metallic bonds are a metal plus a metal. Okay. Metallic bonds are a metal plus a metal. This is kind of true sharing of electrons. My electrons are your electrons. There's no attachment. This forms electricity. And nobody's electrons are moving particularly fast in electricity, even though you turn the light switch on and the light turns on basically right away. This is a domino effect. So it's like you have this giant string of dominoes up your wall, and you turn your light switch, and it boop, 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 and those are your dominoes, and now your light turns on. And electricity is super similar. It's just like my little electron like boops your electron out of the way, and then you boop the next person. Okay, so metallic bonds are really good at sharing their electrons. This is also why metal is bendy, which you don't necessarily think about unless you're doing something like taking the pop tab off of a pop can or something like that, or playing with a paper clip. Metal is bendy. Metal is bendy because of this amazing property of sharing all these electrons. Ionic bonds are not bendy. They are super not bendy. You jar them a little bit and they shatter apart. Metallic bonds actually are pretty bendy. And the things that you think of as being metal are metal. However, they are often kind of like laced with, like they've got a little bit of non-metal stuff in them also to buff them up a little so that they're a little bit less bendy. So steel is iron plus carbon, and that plus carbon is crucial. Like iron itself is much bendier than steel because it's got a little bit of that non-metal in there also. So metallic bonds is true sharing. Ionic bonds is true. I shouldn't even put that in parentheses. It is true giving and taking electrons. So I'll zoom in on that so you can see it too. Because covalent is going to be somewhere in between. So ionic bonds really give away and take electrons. Once the electron is gained or lost, it will probably never go back because it is so much more stable. For metals and nonmetals, if they have been like paired in that way, they will probably, like if they've had the opportunity to exchange their electrons, they will, and then they will stay that way forever. Okay, metallic bonds, like metal atoms in metallic bonds, share their electrons. Everything is wonderful and sharing and great and cool. Okay. Great. Covalent bonds. Covalent bonds are fascinating because they kind of, in some ways, kind of start to run a gauntlet here between, they're the in-betweeny ones. Okay, ionic bonds are a metal and a nonmetal. Metallic bonds are 2 metals. Covalent bonds are 2 nonmetals or more, right? Your covalent bonds, you are more than 2 nonmetals, but at their kind of base form, covalent bonds are 2 nonmetals. And you've probably heard in previous years that covalent bonds are sharing their electrons. Here to tell you now, metallic bonds are sharing their electrons. They do that domino thing where they just kind of like share right on down the line. Covalent bonds are way more like, we do a demo in class where you take your pencil and your neighbor, and you're gonna give your pencil to your neighbor, but you're gonna hold on to it because you still want your pencil too. So our initial idea of what covalent bonds are both you and your neighbor tug of warring on that pencil. Like covalent bonds, we say sharing because both atoms use the electrons, but if they could, each one of those atoms would run off with the electrons and leave the other one stranded, and they're stealing, right? They're both trying to steal. Both atoms trying to steal the electrons. So they both wind up using them, and that's why your middle school teacher says sharing. But really, they want to pull them. And you know from trends and stuff like that, that this corner has really high electronegativity. They have really small atoms, lots of effective nuclear strength, almost full p orbitals. So atoms up here are really strong at taking other things' electrons. But if you get this atom together with that atom, they both want to take each other's electrons, but neither is strong enough to actually do it. It's when you cross this line into the metals, now the nonmetals are just like hands down definitively stronger than the metals. They will take the electrons. But two nonmetals stuck to each other, nobody's really gonna win. You're gonna get these competitions where somebody is a little bit stronger than somebody else. That's polarity. When you've got somebody really strong bonded with somebody kind of less strong, if they're both non-metals, nobody's gonna win this fight. You're not gonna fully form an ion, but kind of the tension of that tug of war, you know, if you've got a really strong atom bonded with like a kind of less strong atom, that's polarity. When you've got like that difference of the pull. You know, this is a tug of war game between, I was going to say a football player and a kindergartner, but that would just be an ionic bond. Somebody would just win that right out. So this is between like a really strong football player and like a less strong football player. I don't know anything about football. Or like a strong kindergartner and a less strong kindergartner. Okay, so like nobody just straight up wins and walks away with whatever the thing is that they want to win. But it's not a fair, it's not sharing. It is pulling and trying to steal. Okay. I'm trying to think of what else I want to write on all of this. Okay. I think those are the big ideas. When we draw covalent bonds, we're going to draw circles around electrons. And that circle is going to show that both atoms are using the electrons. They're both trying to steal. Neither one is fully successful, but it is not a sharing situation. So like both nucleuses get to use the electrons in between. When we drew ionic bonds last week, we draw arrows to show that the electrons are fully gained or lost. Okay, so yeah, I'll zoom in on that also. So ionic bonds draw arrows, just like last week. We've done that a lot by now, to show that the electrons are truly gained and lost. Covalent bonds will draw circles to show that both atoms want those electrons and simply they're both using them. Your middle school teacher's not wrong that they're sharing. That's just not what they want to be doing. Okay. Cool. Let's draw some pictures. Got some concepts. Now let's draw. Okay, so covalent bonds When you draw covalent bonds, we'll draw circles. So, and really what we're showing is the electrons move around both nucleuses. Nucleuses. I spelled that wrong. I don't know how to spell it right. Nucleuses. Cycles. Oh, ratios matter. Okay, so in ionic bonds, we reduced our subscripts to find the lowest ratio. Covalent bonds, we will not. Okay, let's remind ourselves. That's a good reminder. Ionic bonds. Okay, so the other type, right? This is metal, non-metal. These are fully charged. Arrows to show that electrons are gained and lost. Ionic bonds reduce the subscripts to show the lowest ratio of our ions. Okay. Covalent bonds do not reduce those ratios. Okay. While we're on that topic, ionic bond names do not describe charge or subscript. Ionic bond names ionic bond do not state how many. This gets a little tricky because ionic bond names of transition metals do state the charge, but no ionic bond name is going to state how many atoms. Covalent bonds names do state how many. How many, like exactly how many atoms in that molecule. I feel like I'm getting a little bit lost already, and maybe I am. Maybe not. Not sure. What's a good example of this? Oh, all the examples I'm thinking of have. Let's do one more point because I was going to get to this later. But apparently I'm getting to it now, which is just fine. Okay. No, I'm going to start you here. Do some examples here. Get more complex later. Okay. Examples. Okay. Let's start with the example of, that's nice, friendly looking covalent bond. You've got a metal and you've got two nonmetals. You've got carbon is over here, hydrogen. In our realm, hydrogen will act like a nonmetal. Sometimes you can get hydrogen to act like an alkali, but out in the real world, in like in nature, hydrogen usually acts like a nonmetal. Okay, great. And it's because it's so small that even though it's just one proton and one electron, like with your trends, hydrogen is small like the other nonmetals. And even though it's only one proton, since it's only looking at a 1s electron shell, that one proton has enough strength to keep its electron attached and to kind of pull on other things' electrons also. Okay, so carbon, a lot of things are going to look similar to your ionic bonds. Draw the valence electrons the thing starts with. Let's write some steps. Draw Lewis structures. And then draw circles to show covalent bonds. Just like your ions, everything wants a full outer shell of 8 electrons. Keep drawing until everything wants a full outer shell of 8 valence electrons. What would a rule be without an exception? Except, so everything wants a full outer shell of 8 valence electrons, except, it's already in my first example, hydrogen. Hydrogen's biggest shell is 1s. A full 1s is 2 electrons. Hydrogen just wants 2. Hydrogen wants 2 electrons. No more, no less. Okay. I'm going to leave you here today. I'm going to complicate this a little bit tomorrow, but you're like used to that already. Let's do it. Okay, so we have CH4, and we just wrote up above, subscripts totally matter. The ratio of these things matter. So in a covalent bond, we have exactly 1 carbon and exactly 4 hydrogens. And we're gonna read it that way because this is gonna tell us how many of each type of atom to draw. We should maybe even say that here. Draw Lewis structures. Like the ratio tells you how many atoms to draw. Ratio tells you how many atoms to draw. Ratio tells you how many atoms to draw. Okay, so we're going to draw 1 carbon. Check, check. We're going to draw 4 hydrogens. 1. And they're Lewis structures, so each hydrogen comes in with 1 electron. 2, 3, 4. I realize that might have gone a little too fast and a little too clean. I'm like showing you the answer here. But for some things, they will go kind of just like that, where carbon starts with 4 valence electrons. Carbon, we didn't draw any ions for carbon because what we did say is that carbon is the diva of covalent bonding, and it is. Basically everything around you is based on a carbon structure. Plastic, wood, your food. I mean, electricity is not. Okay, so you have to go looking for something like electricity to get something that is not carbon-based. Your paper, your pencil lead, this is all carbon. I don't know why I thought of makeup, but that is all carbon. Virtually everything is carbon. Trees, plants, your dog, your cat. Water is not carbon, but it's stuff like that. Water and electricity are the things I've thought of so far that are not carbon. Even steel has carbon in it, though it also has a lot of iron. But, okay. Carbon makes a lot of bonds. Okay. 4 valence electrons, ratios matter. We're going to draw 4 hydrogens. I happen to very strategically place them in exactly, to make these nice little circles. So draw the Lewis structures. Ratio tells you how many to draw. Draw circles to show covalent bonds. Here we go. We're going to draw. Okay, and what this little circle means is that these particular 2 atoms are bonded together. So this, I'll draw all 4, and then we'll talk about them. So this circle right here shows that these 2 atoms are bonded to each other. So each circle is describing the relationship between those 2 atoms, okay? That circle right there is showing a relationship between these 2 atoms. That circle is showing a relationship between those 2 atoms. Great. And what these circles mean is they mean that both of these electrons, remember from ionic bonds, electrons like to be paired. We didn't go super into that because whatever, but each suborbital holds 2 electrons. That might ring a bell. Your carbon has a 2s orbital, and it has a 2p orbital, and that 2p orbital has 3 subshells. And in the off chance that this made no sense the first time, that's totally okay, and don't feel free to just keep thinking about it, even though I get it. This is even trickier than usual virtually. Okay, so your carbon has a 1s, but that's its noble gas core. It's got a 2s, and it's got a 2p, and that 2p has these 3 suborbitals. These are the 4 sides of your Lewis structure. Each suborbital wants 2 electrons. So when the carbon makes these bonds, it's taking each one of these orbitals and it's filling it. So carbon starts with electrons, 4 valence shell electrons, 1, 2, 3, 4, essentially, effectively. And then, because it makes a molecular orbital, but whatever. Think of it as 1, 2, 3, 4. And when we add these 4 hydrogen atoms, their 1 electron each has added into these 4 suborbitals. And now carbon has a full noble gas configuration because all of its outer shell suborbitals are now filled. Carbon started with 4 valence electrons, 1, 2, 3, 4, and now we've added 4 hydrogens. And when we count carbon's valence electrons in its bonded molecular form, the CH4, we've got 1, 2, 3, 4, 5, 6, 7, 8. That's a noble gas configuration. All right. We drew our Lewis structures. We drew the ratios. We used the ratio to tell us how many atoms to draw. We drew circles to show covalent bonds. Check, check. Do a check. I didn't do that on purpose, say it on purpose, but do a check. Everything wants a full outer shell of 8 valence electrons. Okay, carbon, 1, 2, 3, 4, 5, 6, 7, 8. Except hydrogen wants 2. This hydrogen has 2. This hydrogen has 2. This hydrogen has 2. This hydrogen has 2. Okay, that's most of how to draw covalent bonds. I will complicate your lives tomorrow, but I'm going to leave it with single bonds today. Single bond, you're like, there's 4 bonds here, but if you look at each kind of relationship, there's 1 circle between those 2 atoms. There's 1 circle between those 2 atoms. Tomorrow, I wasn't going to do this, but I'm going to preview tomorrow. We're going to start drawing multiple circles to show atoms can bond multiple times to another atom, but I'll show you that tomorrow. Let's leave it with single bonds here. Cool. I'm going to give you some practice questions to think about. And I'll do another example there, but that is most of your ideas on covalent.